Hello and welcome everybody to today's webinar, Evaluating Tunnel Safety and Ventilation with CFD, brought to you by CONVERGE Science. Thank you for joining us today for this installment of our webinar series. My name is Scott Davis and I'm part of the business development team at CONVERGE Science, and I'll be your host for today's event. We're excited to showcase CONVERGE and its capabilities in tunnel safety and ventilation. CONVERGE Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Our speakers today are Dr. Gregor Schmolzer and Dr. Daniel Fruwitz. Dr. Gregor Schmolzer is a senior engineer at FVT, a research company for internal combustion engines and thermodynamics. Dr. Schmolzer received a PhD from Graz University of Technology with his thesis on tunnel ventilation systems with closed loop control measurements and investigations for successful commissioning. Dr. Daniel Fruwitz is a senior researcher from at Graz University of Technology, focusing on traffic and environment. Dr. Fruwitz received a PhD from Graz University of Technology with a thesis on design and optimization of ventilation and cooling systems in long railroad tunnels. We appreciate them being here today. We'll turn the time over to Dr. Fruwitz first.
So, I hope you can see my screen now.
Yes, you're great. Thank you.
Perfect. So, welcome to my presentation about CONVERGE CFD in tunnel safety applications. Thank you for having me and for the possibility to give you this talk today. What I'm talking about is some research activities from our department, which we did in the past years. And after that, I will switch over to selected projects and selected CFD studies we did recently. One is a Hydra project, which is about hydrogen hazards in tunnels. And after that, I will close with some CFD studies about our full-scale fire test in the Austrian Koralmtunnel. So our research is about safety of transport, in particular about tunnel safety. We do design studies for mechanical installations such as ventilation, fixed firefighting systems, and heating, ventilation, and air conditioning systems. We do full-scale fire tests, and our focus in the past years was on consequences from alternative energy carriers such as batteries and hydrogen. The second field of expertise is air quality. So we are also dealing with consequences from transport, which is mainly related to dispersion calculations. We also do some PM monitoring and monitoring of gaseous pollutants. Here you can see some impressions of our studies. In the images above, you can see our full-scale tests on battery electric vehicles, on the full-scale tests in the Koralmtunnel in the central image, and on the right-hand side, you can see our new gas burner station with a peak heat release rate of 5 megawatt. And we do not only do experiments, there's also a strong focus on numerical simulations. So CFD is a big part of our daily business, and CONVERGE is the tool we are using right now. And today I will present you some selected results of our studies. The Hydra project, which is a hydrogen tunnel risk assessment. It's organized by the FFG, which is the Austrian Research Funding Agency. The funding is provided from the Austrian Federal Ministry of Climate Action, Environment, Energy, Mobility, Innovation and Technology, as well as by ASFINAG, which is the highway operator here in Austria. Our partners are the HY Center, the Hydrogen Center Austria, and ILF Consulting Engineers. Yeah, what is Hydro about? The project tasks are investigations on hydrogen incidents in a tunnel. So the hazards that can be expected from hydrogen incidents. On the one hand, these are jet fires or tank burst or hydrogen cloud explosion. And in order to investigate these scenarios, we do some CFD modeling for selected scenarios and subsequent risk analysis. Today, I'm focusing on a hydrogen cloud explosion. Why is this an important or relevant scenario? Because of the wide flammability limits that hydrogen is characterized by. In the range of 4 to 76 volume percent, you have a flammable mixture with a volume fraction of more than 20%. The deflagration to detonation transition is likely to occur. So this is related to the overpressure that can be expected inside a tunnel. And when comparing these overpressure with harm criteria, you can imagine that is worst case scenario, let's say. I have depicted some harm criteria right here taken from the High Response project, which is an EU-funded project. You can see 8 kilopascal is the limit for no harm. With 13.8 kilopascal, you can have an eardrum rupture. With more than 80 kilopascal, this is the threshold for lung hemorrhage, and some more threshold values or ranges that that are depicted here relate to fatalities and immediate fatality, let's say. So you can imagine it's very important to evaluate the hydrogen concentration in the case of an unignited hydrogen release in a tunnel. We do assume that it's unlikely that hydrogen is released unignited, but it cannot be ruled out. So we do have to evaluate the possible hydrogen concentrations in a tunnel. But before I come to the tunnel case itself, a short introduction about hydrogen passenger cars itself. How is the setup of such a car? You do have a high voltage battery on board. You do have a hydrogen tank system on board. Here the case is the Hyundai Nexo. This car has 3 hydrogen tanks with a total mass of roughly 6 kilograms of hydrogen. You do have a fuel cell system and an electric powertrain. So these are the main components of this system. The storage pressure for hydrogen is 700 bar, as it is common for passenger cars. And for safety reasons, the hydrogen tanks have to be equipped with a TPRD, which is a thermal pressure relief device. So thermally activated in order to control the pressure inside the tank vessels. There's this is a safety device which opens a flow path as soon as 170 centigrade are exceeded. So hydrogen will be released, and this is an irreversible opening, so no reclosing anymore. On the top right hand side, you can see the general layout of such an TPRD, and on the bottom right you can see the orientation of the release. So it's downwards to the back on an angle of 45 degree. The size of such a TPRD depends on the tank size, so but it is in a range of 2 to 5 millimeters. Yeah, in order to investigate the hydrogen release in a tunnel, the tunnel itself had to be defined for the numerical study. On this slide, you can see the the geometry that was used in our study. We have a 200-meter tunnel section. The very simplified vehicle model was situated 80 meters from the inlet boundary. The cross-sectional area is roughly 60 square meters, which is more or less a standard 2-lane tunnel, and the 45-degree release direction was taken into account. As you can imagine, 2 to 5 millimeters diameter of the DPRD. This is quite a challenge if you have a computational domain that is 200 meters long, 9 meters wide, and so on. So the DPRD was chosen to be enlarged to 5 centimeters. It is assumed that this is not critical in our case because we are not interested in a detailed modeling of the outlet jet, but we are interested in a dispersion inside the tunnel. And as soon as you have an impingement of the hydrogen jet on the road surface, the inlet momentum is significantly decreased. So yeah, this simplification is assumed to be valid. Based on this geometry, we did the meshing. CONVERGE provides a series or a variety of features and tools for an excellent meshing. We defined a base grid of 0.4 meter cell size, and we employed a fixed embedding, a 3-step fixed embedding. So one step is the section around the car model. Another refinement was done for the area here in the back of the car, and the further refinement was employed in the area below the car body. In addition, we employed an inlaid mesh in order to have a resolution or an accurate resolution of boundary layers. And this is the main benefit in my opinion, or to my opinion. The adaptive mesh refinement is a powerful tool. So we used it for do refinement steps during the simulation, and this adaptive mesh refinement was based on a velocity gradient criterion. It was a 2-step refinement, actually. The solver setup, some key facts about this. We used the Reynolds averaged Navier-Stokes approach. As a turbulence model, we selected the standard K-epsilon model in combination with the enhanced wall treatment, and the PISO algorithm was also employed. As we were only interested in the hydrogen distribution, no chemical reaction was taken into account, and heat transfer was neglected. The boundary conditions, here you can see 2 of the most important boundary conditions. On the one hand, blowdown model was needed. We did some pre-calculation with an analytic model provided with HiRAM software, which is an open source software. We did some calculation about the flow rate of hydrogen throughout the TPRD. In the case of 700 bar, 69 liter tank size, and 2.25 millimeters TPRD size. So this curve was applied on the inlet boundary at the TPRD. And on the other hand, the second very important boundary condition is the airspeed at the inlet and the inlet portal, let's say. And here you can see a transient profile. So initially you have an vehicle initiated or traffic initiated airflow in a tunnel, which is about 5.7 meters per second. And with the stop of the traffic, the airspeed is decreasing down to roughly 2 meters per second after 300 seconds. So these boundary conditions were applied on our model, and in total we did 4 CFD scenarios, 1 with this transient airspeed profile, and 3 more scenarios that are derived from the Austrian standard for tunnel ventilation control. The Austrian standard, the RVS, foresees a minimum of 1 meters per second in bidirectional traffic mode and a maximum of 2 meters per second in unidirectional traffic mode. In addition, we did a worst case scenario, which is about 0 meters per second, so no tunnel airflow at all. Yeah, now coming to the results, here you can see the impact of the supply air velocity. At the top, you can see the results for 0 meters per second, or roughly 0 meters per second. You can see hydrogen distribution in both directions. So the tunnel airflow would be from left to right in all these cases. And you have a more or less symmetric dispersion or propagation of hydrogen and the hydrogen cloud formation at the ceiling. And yellow areas represent regions with hydrogen volume fraction above 4%, so a flammable cloud, let's say. So with no airflow in a tunnel, you have a long distance or a long or big hydrogen cloud in a tunnel, and definitely an explosion risk. With increasing of the supply air velocity to 1 meters per second, you can have let's say a better situation. The hydrogen is more or less only present in the downward section of the tunnel, so downward from the release point of release. But you still have some sections and some regions where a flammable cloud occurs. And the further increase to 2 meters per second has the advantage of dilution of the hydrogen, and there are no let's say relevant sections with a flammable hydrogen air mixture at all. So you can see ventilation has a strong impact on the hydrogen cloud formation and a strong impact on the safety in this case. Yeah, the conclusions were that hydrogen cloud formation after an unignited release in a tunnel requires mechanical ventilation. With no ventilation, we would have cloud lengths up to 200 meters after the tank being the tank is released, and we do have regions with more than 4 volume percent. Actually, we are close to the detonation limit in the very top layers, and with increasing of supply air velocity, we can prevent from flammable cloud formation, and definitely we are far away from the 20 volume percent limit, which is related to the detonation of such a cloud. So it seems that the ventilation strategy according to RVS seems sufficient. Yeah, now I'm switching from hydrogen to our full-scale tests in the Austrian Koralmtunnel. This is we did these tests in 2017, so some years ago. Were full-scale tests with heat release rates up to 21 megawatt. At this slide, you can see the measurement setup. So we had this sheltered box here, equipped with some pools. In these pools, fuel mixture of diesel and gasoline was filled. So we had roughly 1.5 to 2.5 megawatt per square meter. And we did some tests with only 2 pool fires. The large ones were with 10 pool fires. And we did lots or extensive thermal measurements. So we had many temperature sensors applied directly at the sheltered box and as well downstream in order to record or to monitor the temperature stratification, to have an indicator for smoke layers, let's say. Yeah, and we used this experimental data we gained from these experiments in order to validate our numerical models we generated in CONVERGE. And we did some validation work based on fire test 7. Fire test 7 was characterized by 8 pool fires. We had a peak heat release rate of 19.5 megawatt and an average heat release rate of 14.5 megawatt. The average supply air velocity was 1.25 meters per second, and we had a maximum back layer of 160 meter. So I should give some information how we do the measurement for that. We had weighing of the pools, so the fuel consumption rate was monitored. We had some ultrasonic anemometers upstream of the fire source, so we had the supply air velocity, and we did some visual observation of the back layer length using marks on the ground we applied before. On the bottom, you can see some impressions of these fire tests, and on the right-hand side, you can see some results from the experiments. So we had a well-defined temperature stratification with low temperature at the bottom surface on the ground and very high temperatures on the ceiling. And yeah, we did some CFD modeling using CONVERGE. You can see the geometry as well as the mesh. The geometry comprised a 300-meter tunnel section. The sheltered box was modeled. We had the pool fires in this sheltered box, and we had some rock layers around the tunnel cross section because we wanted to have an accurate heat transfer to the solid layers, to the rock, concrete and rock actually. So we had to model some solid layers as well. The fire modeling itself was done with a reaction chemistry model using isooctane as a fuel, which has very similar property values than our fuel mixture has had. The solver setup was included a Urans approach. K-epsilon model was employed in combination with standard Wolf function. The simple algorithm was employed. We also modeled the radiative heat transfer with the DO radiation model, and conjugate heat transfer was activated. The mesh generation tunnel section itself is, as explained, 300-meter long, 10 meters high, and 10 meters width. The base grid was defined by 0.8 meters cell size, and we had a 2-step adaptive mesh refinement for temperature based on a temperature and velocity criterion. The sheltered box itself was modeled by thin elements that only allowed for 1D conjugate heat transfer. Yeah, and the results showed that we captured the maximum temperature at the ceiling very well. We had roughly 250 centigrade at the ceiling. Here you can see the temperature profiles as a function of time. So single curves relate to a certain point of time during the test. And you can see the temperature stratification was present in the experiments as well as in the numerical study. I would say it is not a perfect fit, but it's a quite good fit. So we were very satisfied with these results, and this was also due to the perfect approximation of the back layer length. So in the experiments, we observed 160 meters, and in CONVERGE, we got 155 meters, so a deviation less than 5%, which is quite good for such an application. Yeah, thank you for your attention. Here you have some references that were provided in my slides, and I would be happy to answer some questions. If you have some, please let me know. My email address will be made available. Thank you.
I would like to welcome you to my presentation on the topic evaluation of jet fan performance in tunnels using CFD. At the beginning, I want to introduce myself a little bit. My name is Gregor Schmölzer. I'm a mechanical engineer and I'm working as a senior engineer for tunnel safety and ventilation at the research company for internal combustion engines and thermodynamics, which is a spin-off of the Institute of Thermodynamics and Sustainable Propulsion Systems at the Graz University of Technology. And my main working areas are the design and commissioning of ventilation systems for especially road, but also rail tunnels, a wide range of aerodynamic measurements, especially in tunnels, fire or hot smoke tests for commissioning, and simulations, one dimension or three-dimensional, and also site supervision and risk analysis for road tunnels. So what I would like to show you today is one of the major problems during the design of a ventilation system, finding correct input parameters for one-dimensional calculations, since we have to do a lot of calculations during the design stage of a tunnel. We can only do this in 1D, and so we need good input parameters, and it is not possible to do always three-dimensional simulation, especially for wider ranges of the tunnel. And one of these problems we are facing during the design of our ventilation system is that jet fans are used for longitudinal and/or transverse ventilation systems. And the main function of these jet fans is to control the longitudinal flow in the tunnel. During normal operation, to provide sufficient fresh air in the tunnel, and in the case of an emergency, to confine the smoke propagation and ensure a defined smoke extraction. And jet fans are used for transforming the momentum out of the jet fan to the surrounding air in the tunnel. But these jet fans, owing to lack of space in a tunnel, are usually installed quite close to the tunnel wall or even in special niches to get enough space to install these jet fans. Here are some pictures. This left one is a classic installation in a longitudinal ventilated tunnel, and as you can see, the jet fans have to be installed quite close to the soffit. In semi-transverse or transverse ventilation systems, we have a false ceiling in the tunnel. Here you can see the false ceiling in the right picture. Above this false ceiling, there are air ducts for fresh air and/or exhaust air. But to influence the extraction of the smoke, we have to install large jet fans in the tunnel and have to build special niches in the tunnel to have enough space to install them. And as you can already see, the installation is not quite easy. So we have, due to this unfavorable installation situation, losses, and these losses are due to increased wall shear stress and momentum transfer from the high jet velocity to surrounding airflow in the tunnel. And these losses are commonly considered by a so-called installation efficiency factor. Here, a short formula. Here you can see this is the effective thrust in the tunnel, and the effective thrust is more or less the jet fan thrust, so the static thrust measured on a test bench at the manufacturer's shop. And this is corrected by this term, mainly the influence of the speed difference between the jet itself out of the jet fan, and the tunnel air, the background velocity in the tunnel. And it's also corrected by a second coefficient. This is the installation efficiency factor called eta. And commonly used installation factors were derived by Kempf, Rone, or Armstrong some years ago, and they were all derived from small scale measurements, so little small tunnels with small, so to say, jet fans at different positions. And so these installation factors were derived, or in some cases they were also derived from numerical studies. But measurements during the commissioning of real tunnel ventilation systems showed quite remarkable discrepancies between the effective measurable pressure increase in the tunnel compared to the original design values. So we did during commissioning a lot of measurements and also numerical simulations in order to investigate these installation efficiency for common installation setups. Just a quick view on the physical background. What you can see here are the so-called formulas or by Meidinger, so to say, defining the jet fan theory in a tunnel. So the theoretical pressure rise due to active jet fans in a tunnel is more or less the momentum of the jet fan multiplied by the number of active jet fans divided by the cross section of the tunnel itself, and corrected by this factor that we already have seen, which defines more or less the influence of the relative speed between the jet fan or the jet coming out of the fan with high velocity and the lower air velocity, background velocity in the tunnel. So that's the theoretical thrust, that the maximum that we can get by a jet fan. But since we have losses, we have to introduce this eta, this installation factor. So the effectively measurable pressure rise in the tunnel, according to active jet fans, is the theoretical thrust multiplied by this installation efficiency factor. And if we multiply this pressure rise we can measure in the tunnel by the cross section of the tunnel, we get the effective thrust in the tunnel. So what we did were some quite simple numerical studies. And concerning the geometry, as you can see here, a screenshot of the chosen model, we modeled a straight tunnel section with a so-called horseshoe profile with a total length of 350 meters. The cross section of this tunnel is about 72 square meters. And we also modeled a pair of jet fans, so two jet fans at the same longitudinal place in the tunnel, installed pairwise with a distance of 50 meters from the inlet and a distance of about 250 meters to the outlet. Each of these jet fans has a static thrust of about 1,200 Newton at a reference air density of 1.2 kilogram per cubic meter. The outlet velocity following the manufacturer's data sheet is 33.4 meters per second. As you can see here, since the complete domain is absolutely symmetric, we used a symmetry boundary here to save computational time. The jet fan itself was modeled with some simplifications. Here you can see some shop drawings of the original jet fan. We did not model the mounting elements connecting the jet fan with the tunnel wall, so these parts were neglected. And it was assumed that the outer diameter of the jet fan is constant. So there's no change in diameter between the central part of the fan and the silencers. As you can see here in the shop drawing, we have the silencers with a little bit bigger outer diameter than the central part. This was neglected. Concerning the grid and the meshing, we used a base grid size of 0.3 times 0.3 meter. And here you can see the base grid here. And in the close proximity of the jet fan, the grid was refined with a fixed embedding with 0.075 times 0.075 meters. And the direct area of the momentum source in the jet fan itself was even more refined with a fixed embedding with 0.019 times 0.019 meter. So this is this area here. And the first refinement stage is here in the close proximity, and the center part of the jet fan where the momentum source is installed. So there is even more finer refinement. On the tunnel wall and the floor of the tunnel, we use the inlet mesh. So that the Y plus, the dimensionless wall distance, is so all fulfillments are all requirements are fulfilled. So the first layer, due to the air velocity in the tunnel, was chosen with a height of 0.015 meters and with 5 layers and an expansion ratio of about 1.5. The same was used for the outside of the jet fan surface. But since in the inside of the jet fan much higher air velocities occur, the first layer was chosen with 0.004 meters. But we also used 5 layers and an expansion ratio of 1.5 for this inlet mesh. And additionally, we used one of the big advantages of CONVERGE CFD. We used an adaptive mesh refinement, AMR, for the velocity with a subgrid scale SGS criterion of 0.1 meters per second. So as you can see in the areas where high gradients between the neighbored cells occur, additional cells are introduced by the software itself during the simulation process. So the total cell count ranged then from 950,000 to 1,600,000 during the simulation due to the adaptive mesh refinement. A short overview over the chosen solver settings. We used a Reynolds average Navier-Stokes approach, and as a turbulence model, we used the K-epsilon realizable model, since these should be more suitable for the widening and expansion of a jet in the tunnel. And we used a pressure-based piezo solver, and heat transfer was neglected. And for near wall treatment, we used the enhanced wall treatment. A short overview over the used boundary conditions. For the inlet, we used a constant velocity in X direction and fixed ambient pressure and temperature. And for the outlet, a constant static pressure and fixed temperature. For tunnel wall or floor, it's more or less the same. We used a law of wall approach with an absolute roughness of 0.025 meters. And the jet fan surface itself was considered as hydraulically smooth, so the absolute roughness was set to 0. And then in the jet fan, we modeled a momentum source in X direction, and this momentum source was controlled or is controlled by a user-defined function, so that the momentum or thrust is corrected at any time based on nominal condition density, for example, or maximum outlet velocity. So this slide shall give you a short overview how we tried to evaluate the results then from the simulation. Here you can see the domain, the 350 meter long tunnel section. Here you can see the symmetry which was used, and here we have, so to say, at X is 0, the pair of jet fans. 50 meters before we have the inlet, and 250 meters downstream we have the outlet. And here you can see already one of the results, that's the differential pressure over the length of the tunnel section. This is the position of the jet fan, and as you can see, between point 1 and point 2. We evaluated the cross-section averaged statical pressure at both points and built the difference, and that is our measured pressure rise in the tunnel due to the active jet fans, delta P 1, 2. And the complete evaluation is a three-step process. The first is a quite simple one. It is used to determine the friction losses in the tunnel without any active jet fans. So the jet fans were, so to say, deactivated, and only the background velocity was flowing through the tunnel section. So we have the friction losses in the tunnel. In a second step, we started the same simulation, but with active jet fans, and then we get this result here. That's the pressure rise due to the active jet fans in the tunnel, delta P 1, 2. And now you have just to add the friction losses to the measured or measurable pressure rise in the tunnel, so that you have the corrected pressure rise, which is caused by the active jet fans. And if you multiply this value with the cross-section of the tunnel, you get the effective thrust in the tunnel. And the theoretical thrust is more or less, so to say, the momentum of the jet fan, and you have to multiply it with the number of active jet fans. So that's more or less the static thrust under special conditions. And then we have this last term here to correct the static thrust of the jet fan. So that's already the already known ratio between the speed in the tunnel, the airspeed in the tunnel, the background velocity, and the outlet velocity of the jet fan. It's here called psi, and so we get the installation efficiency factor by dividing the measured, so to say, effective thrust in the tunnel by the number of active jet fans, the static thrust per jet fan, and the correction unit for the relative speed between the jet and the background velocity in the tunnel. And here are already the results for this special case. So the parameters we evaluated from the simulations, the friction losses were, since we only had a very low airspeed in the tunnel, about 0.58 meters per second, the friction losses were only 0.1 Pascal. The measurable pressure rise with active jet fans was about 23.7 Pascal, and this will be corrected. So in total, it's 23.8 Pascal. The air density in the calculation domain was 1.12 kilogram per cubic meter, and the outlet velocity, the averaged outlet velocity in the silencer of the jet fan is 30.51 meters per second in the simulation. The cross section of the tunnel is 72 square meters, and the outlet area of the jet fan is roughly about 1 square meter, and 2 active jet fans were used during the simulation. So when we calculate now our values with these parameters, we get an effective thrust in the tunnel of about 1,726 Newton, and the static thrust corrected by air density and relative speed in the tunnel for one jet fan is 1,040 Newton, and the correction factor for the relative speed is 0.019, and so we get an installation efficiency coefficient of about 85%, 0.847. So what we did was some time before we did these investigations with CFD, we did a full-scale measurement of exactly this setup in a tunnel research center in Austria, and the measurement has shown an installation efficiency of 82%. And we compared the results with similar investigations from the past that was done at our institute, but with other CFD packages. which shows coefficients between 0.84 and 0.85, so 84 to 85%. So nearly the same as we got as a result with this study. So here you can see finally some pictures of the measurement campaign. Here, the jet fans in the research center, and this is the measurement device we used to measure the velocity in the outlet of the jet fan. And here you can see some tables out of this paper from a former colleague of mine, Michael Bayer et al. From 2016, where a large amount of such installation coefficient efficiency coefficients were derived from numerical studies done with 3D software, 3D CFD software. And here you can see for our setup, these are the yellow marked points here. We see coefficients between 84 to 85%, so nearly the same as we got in our investigation here with CONVERGE. So the first results fit quite good and seem quite reasonable, but further cases shall be investigated in the near future. So last thing I want to say is thank you for your attention. And if there are any questions, please don't hesitate. Here's my email address. So if there are any questions, just don't hesitate to ask. Thank you very much.
Great, thank you so much, Dr. Fruwertz and Dr. Schmolzer, for your presentation today. You've done a wonderful job, and we really, again, thank you for your preparation and the delivery of your presentation. For those that you would like additional information about this presentation or any other webinars in our webinar series, you can use either one of these QR codes to reach out to us. If you'd like to receive our newsletter, you can use the QR code on the right side. We'd also like to invite you to join us for our next webinar, Harnessing the Power of CFD for Marine Engineering. That will be August 3rd, 2023. So please put that on your calendar and join us for that webinar. We really appreciate you joining us today. And as we mentioned, please reach out with any questions that you may have. Have a great day.